a 1-butyne, and we're asking how can we make a 6-carbon ketone? Well, analyze the problem. What do we need? We need to add 2 carbons. The only way that we know to add carbons is our C triple bond C anion plus an alkyl halide. Okay, and then if the only way we can add carbons is using an alkyne, that's fine. We can get to a 6-carbon product, but then how do we get from this 6-carbon alkyne to the ketone? And since that alkyne will be a terminal alkyne after we add carbons, we have one of 2 methods to turn an alkyne directly to a ketone. We can use acid-catalyzed hydration of an alkyne, or hydroboration oxidation of an alkyne. Okay, so let's work that out. We have the 1 carbon, or the terminal butyne, that's 4, 3, 2, 1. I'm going to add 2 carbons, and so in order to be able to add 2 carbons to the butyne, I first need to deprotonate. My reagent for deprotonating is sodium amide, NaNH2. Okay, after I deprotonate, then I need to go from 4 carbons to 6 carbons. So that means I need a 2-carbon alkyl halide. So step 2, I'm going to have ethyl bromide. All right, and that will give me the 6-carbon alkyne. So I need to add 1, 2 carbons. Notice that it is a symmetric alkyne, so it will produce only 1 product. From the 6-carbon alkyne, I can make the alkyne into the ketone by either acid-catalyzed hydration or hydroboration oxidation. So I need to write out the reagents for those reactions. So I put H2SO4 and H2O, and that should give me the desired 6-carbon ketone product. So looking at your book's suggestions, they're saying, okay, the product can be obtained from 3-hexyne, and that's the alkene that we made, 3-hexyne, alkyne that we made, 3-hexyne. So we have our 3-hexyne, And through acid-catalyzed hydration, we can make the desired ketone. The 3-hexyne can be prepared from the 1-butyne by taking sodium amide and ethyl bromide to make the 3-hexyne. So this is the exact same series of reactions that I went through on the previous slide. 1-butyne, sodium amide over ethyl bromide, giving the 3-hexyne. The 3-hexyne treated by acid-catalyzed hydration, giving the ketone final product. All right, more reactions. Okay, so what are we doing here? Analyze the difference between the final product and the product the starting material. So in the final product, we have 5 carbons. We start with 2 carbons. So if I focus on the first 2 carbons, how do those 2 carbons differ from the alkyne? I have 2 less pi bonds, so minus 2 pi, and what do I get in exchange for pi? I get 2 bonds, carbon 1, so C1 gains 2 bonds to hydrogen, and C2 gains 1 bond to hydrogen, 1 bond to bromine. So 1 pi bond is used to make 1 bond to hydrogen for each for each electron, and the other pi bond is adding 1 hydrogen and 1 bromine. So how do we do a reaction with an alkyne where we add only 1 halide? There are a couple of things that I could think of. So we have a few options. For example, I know that in the first step, the only way to add carbons to the alkyne is to use sodium amide. Deprotonate that, and then add an alkyl halide with the desired number of carbons. So on step 1, I'm going to add sodium amide, and I need 3 more carbons, so I'm going to add on step 2 propyl bromide. The 3-carbon halide. And that will give me the 5-carbon alkyne. Oops. So, 1, 2, 3, 4, 5. Okay, so we have our 5-carbon alkyne. And now I want to take my 5-carbon alkyne, add 1 bond to hydrogen and 1 bond to bromine, and then add, take the other pi bond and add bonds to hydrogen to each carbon. So the options are that I could first make the alkene, and then from the alkene, add HBr. So I could treat with Lindlar's catalyst and H2, and that would give me the 5-carbon alkene. And then I could treat the 5-carbon alkene with HBr to get the 2-bromopentane. Or I could take the 5-carbon alkyne, alternate route, treat with 1 equivalent of HBr so that I get the alkene that has 1 1, 2, 3, 4, 5. So now I have the alkene with bromine added. And then I can treat that with H2 in PDC, palladium over carbon, to get the 2-bromopentane. So there's more than one route. Usually to get to the final product, you have more than one pathway to achieve that desired final product. And both answers would be correct. What you have to figure out when you're doing research in a lab is which process provides the highest yield. We can't know that just proposing the syntheses on paper. But when you want to make something experimentally, you have to try multiple methods and determine which one is the most cost-effective and gives the greatest amount of product. All right, so what the process that I just went through, your book calls retrosynthetic analysis. So in their retrosynthetic analysis, they take the 2-bromopentane and they highlight the first 2 carbons, because those carbons they are proposing come from the ethyne. Okay, and so then they're saying we can make the bromide from the alkene, we can make the alkene from the alkyne, and we can make the 5-carbon alkyne from the 2-carbon alkyne. So then, once they have done this analysis of functional group transformations, the alkyl halide from the alkene from the alkyne, and the 5-carbon alkyne from the 2-carbon alkyne, they'll go back, starting with the 2-carbon alkyne, and put in the reagents required to go from 5 to 2, from alkyne to alkene, and from alkene to alkyl halide. So by their analysis, the method that they picked is the 2-carbon alkyne, reacting with sodium amide to deprotonate, and adding our 3 carbons to get to our 5-carbon alkyne. The 5-carbon alkyne was treated with hydrogen gas and Lindlar's catalyst to produce the alkene. The alkene is reacted with HBr to produce the alkyl halide final product. Okay, looking at another example. Designing a final synthesis. So we're going to start with a terminal alkyne of undetermined number of carbons. And so you have to pick a position in your final product where there is the potential to have a triple bond. The only positions that have the potential to have a triple bond are between 2 CH2 groups, proposing that we have added 4 hydrogens. So we can have a triple bond between these two carbons, an orange square, or between the two carbons in the green square. Triple bonds can occur between secondary carbons. They cannot occur at a tertiary carbon because a tertiary carbon has 3 bonds to carbon, where an alkyne can be only primary or secondary. So if you look at the alkyne, two examples of what an alkyne is. For a terminal alkyne or an internal alkyne, because of the nature of the triple bond, the highest number of possible bonds to carbon are 2. 1, 2. 1, 2. So alkyne carbons can only be secondary, or in the case of the terminal alkyne, we could have 1, 1, 2 bonds to carbon, or for the terminal carbon, only 1 bond to carbon. So that gives us a primary carbon and a secondary carbon at best. That means that in your final product, you have to pick carbons which are primary or secondary for the position of the triple bond. So we can rule out the possibility that the tertiary carbon could be part of the triple bond. Okay, so my initial alkyne, we can have 2 options. I could have my orange option, where my triple bond is between the 2 carbons that are in the orange square, or I could have my green option, where my triple bond is between the 2 carbons in the green square. And I have to pick which one. Now that means that for the green option, the other half of the molecule would be this blue section. Okay, so those 2 pieces need to be combined in order to make the final product. How am I going to add a new carbon-carbon bond? Well, this blue section, new carbon-carbon bond, can only be added using an alkyl halide. And so at the position where the new carbon-carbon bond from the green to the blue would occur, I need to have a halide bonded to that carbon. The same thing for the orange carbons. For the orange carbons, I have, when the triple bond is between the orange carbons, then this purple section are the carbons that have to be added to the orange carbons to make the final product. And so I'm going to need an alkyl halide on the carbon that the orange carbon bonds to, and to draw the rest of that structure. So now we have our two possibilities for how we can form our final product. So in order to do this, I'm going to need the alkyl halide to be step 2. So, all right, so for the orange, I'm going to redraw it skeletal structure wise. So there's my orange section. And for my process, I'm going to first add 1 sodium amide to deprotonate. Then on step 2, I'm going to add the alkyl halide proposed in purple. So bromine bonded to a CH2 group that is bonded to a branching carbon. So that gives us our 4-carbon purple fragment. We combine them to produce our alkyne. And then I can treat this with H2PDC and remove all pi bonds. And I'm going to squeeze that in, pointing up, to show that it goes to that product. So let's read through this and see if it matches. We have a CH3 group here, and what our final product would give us would be a CH3 and a CH3 bonded to a CH. CH3, CH3, CH. Then this, when treated with H2PDC, will become a CH2 group, CH2 group. This carbon will become a CH2 group when treated with H2PDC. There it is. Then we have another CH2 group right there. We have a CH group. There it is. And CH3 and CH3 here and here. So our skeletal structure would match the structure drawn as the final product. We can go through this also with the second option. So I can take my alkyne, my green alkyne, treat with sodium amide 1 and 2 with my blue alkyl halide Let me just move this over here. And then zoom in to treating with my blue alkyl halide. And when I combine those two, I can have CH3, CH, CH3, CH2, green, C, triple bond C, single bond CH, CH bonded to CH3, bonded to CH3. Then if I treat this with H2PDC, H2, comma, palladium over carbon, that will give me my desired alkane. CH3, CH, CH3, CH2, C, H2, because I have removed the triple bond, CH2, CH, CH3, CH3. And that should match the product that they requested from us, the 2,6-dimethyl heptane. So those are their two methods that we could make, by which we could make 2,6-dimethyl heptane. And when they put the R group on our terminal alkyne as shown, that means that we get to choose what our starting material looks like. Are we going to pick the orange starting material or the green starting material? It's up to us. Okay, so of course your book does the retrosynthetic analysis as well. And their analysis, they picked the carbons that I had circled as green. So the second option that I showed. And they took those two carbons, two CH2 groups, and added the triple bond. So the alkane can be made from the triple bond, basically. And so we can have, if the triple bond is at this position, we still actually have two options on how it's made, because we could break it at this position or this position. So in reality, I showed you two options, and those two options had the alkyne at a different position. But in reality, there are probably 4 different ways to make the final product. So if the alkyne is at this position and they break it on the right side, then we're going to have our alkyl halide as the isopropyl bromide and our alkyne as this 1, 2, 3, 4, 5, 4-methyl 1-pentyne. And if they break it at the left side of the triple bond, then we will have a 3-methyl butane, 1-butene, reacting with an what they call isobutyl bromide, or 1-bromo 2-methyl propane. And then from there, we can perform retrosynthetic. We can go forward towards the final product. So looking at the first case with the 4-carbon alkyne, they take their 3-methyl 1-butene, react it with sodium amide, followed by the 1-bromo 2-methyl propane to make the 2,6-dimethyl 3-heptene. The 2,6-dimethyl 3-heptene is treated with H2PDC and produces the 2,6-dimethyl hexane. Okay, sorry for the pause. So that gives us that final product. Ooh, that's a really long video.